Yes, so as you can read, I will tell you something about the all-electron full potential linearized augmented plane wave method. And you might imagine that this could be of relevance for the workshop. And this is actually true, but what I'm going to tell you will not be a big topic in the hands-on sessions. So the hands-on sessions will be about how to perform certain types of calculations. And this talk is more about how to make sure that your calculations are good calculations. Yeah? So this is about parameters and so on. So let us have a look at the outline. And so I will hold the talk in a practical way. So I will focus on the practical aspects of LAPW. And well, first I will look at the theoretical practical aspects. And this is about the LAPW basis that I'm going to introduce. I will tell you a little bit about the separation of the core electrons from the valence electrons, and I will also say a little bit about the representation of the density and the potential. And it would be a good idea to focus on the parameters that I mentioned there. Next, I will focus on how the parameters affect the calculations, how to set them, and so on. And then I will go into more detail into how to use FLIR. So I show you the input file and so on and so on. And in the end, I give you some ideas for further reading and conclude the talk. So let's start with the theoretical background. So to attach this talk to Mariana's talk, let me first provide you some pointer at what actually LAPW means in comparison to other methods. So the LAPW stands for linearized augmented plane waves. This is a basis set. And this, well, you heard about the representation of the wave function, like Gaussian orbitals and real space grids and so on. And you know, the LAPW is a linearized method, so there's a linearization in it. That's an approximation. Yeah. But we can control this approximation. You will see. And if you look at the Kohn-Sham equations here, then there are many aspects of how to realize certain aspects of this. For example, the kinetic energy operator, the kinetic energy, how is it calculated? It's calculated in a non-relativistic way, in a scalar relativistic way, in a fully relativistic way. In FLAPW, we have all of that, depending on the regions and on the energy. So we adapt the degree of relativity on what we want to describe. Of course, the exchange correlation potential you can calculate with different approximations, like local density approximation, TGA, LDA plus U, and so on and so on. And in DFT codes, you can exchange these approximations, and also in FLIR. And when it comes to the potentials, there are certain approximations. You heard about a pseudo-potential approximation, and well, we have a very sophisticated basis set, the LAPW basis set, with which we can treat all electrons within a material, and so we don't need this approximation. And also, we don't need some spherical approximation, which was, well, some decades ago very common, but we treat the full potential. So let's have a look at what we actually want to represent. So we have some potential. This is a periodic potential, the blue thing here. And now we want to describe a wave function there. And if we look at very low energies, the wave function is very localized. But if we go up in energy, then the wave function tends to get nodes. and also is less localized. And if we go to even higher energies, then well, it is not really localized anymore. But well, it's stretched out to also the other atoms, I would say. But we need actually more than that. But let's first name these different wave functions and electrons. So with these energetically low-lying electrons, we call core electrons. Then you heard about the semi-core electrons, and in the upper part here there are the valence electrons. But of course, in a crystal, there you have the Bloch theorem, and therefore we have some Bloch factor times some periodic function, and the wave function actually looks like this. So how can we actually nicely represent this? So in the LLPW basis, well, what we do, we partition the space into different regions. So we have these muffin-tin spheres around each atom, and they are nearly touching. And in between these spheres, we have an interstitial region. And we have different representations of the wave function in these regions. So in the interstitial region, we have plane waves. You directly see the Bloch factor here. And in the muffin-tin spheres, we have radial functions, u and u dot, times spherical harmonics. And these u functions are actually solutions to the radial Schrödinger equation at a predefined energy parameter, EL. Yeah? And this u dot is the energy derivative of this. And of course, these representations in the different parts of the unit cell are not independent of each other, but we use these A and B coefficients to match the muffin-tin part of the representation in value and slope to the interstitial plane wave. Yeah, so in the end it looks like this. Yeah? So here you can already see some parameters. So this is a single basis function that you see here. And of course, we only can deal with finite basis sets. So we need to have a cutoff parameter. So that says we don't use more basis function. And this cutoff parameter is k max. We call it k max, which is k plus g max. You see it here, k plus g. And yeah, it basically defines the basis set size that you use. Then you see some L max. Well, you don't see it, but actually it is the upper boundary of this sum here. So this angular expansion, the muffin-tin spheres, also has to end somewhere. And we ended with this L max cutoff parameter that we can also set in the input file in the end. Then you see that there are certain numerical parameters like the muffin-tin radius. Of course, well, this representation in the muffin-tin is only in the muffin-tin, and therefore you have to define how large the muffin-tin is. And this is done with by specifying this muffin-tin radius. And there are also these energy parameters that you need to determine the u and u dot functions. And well, we can also set them before the calculation. Or we can set a recipe how to calculate them. So let me give you one remark here. So, and this remark is for the third talk today, and by Christian about forces and necessary functional perturbation theory. And he asked me to mention that the LLPW basis depends on the atom positions. And of course, this is pretty clear. The muffin-tin radii are centered at the nuclei. And if you move the nuclei, the muffin-tin spheres move with them, right? And also, the LAPW basis has discontinuities. So this Lmax cutoff is finite, but of course, if you expand a plane wave in terms of spherical harmonics times radial functions at the Muffin-Tin sphere boundary, then well, this expansion is not finite. Yeah? So we have some discontinuities here, but we will see about that later. So Marianne already told you that we deal both with the valence electrons and also with the core electrons. And to be able to do this, the LAPW basis has to be orthogonal to the core electrons, because otherwise we would set up some Hamiltonian in the LAPW basis and also overlap matrix, and then we would solve this generalized eigenvalue problem, and we get eigenvalues that suddenly describe the core electrons, and this is something that we don't want to be. We don't want to see, and therefore we have to have such an orthogonality. And so I will sketch a proof that this actually is the case. So consider the radial Schrödinger equation that is used to actually calculate these U functions, and let's also imagine that they are used for the determination of these core wave functions that I call here ULC. So you can write this down, and you can actually, so this is the function for U. You can multiply it by R times ULC on the left, and if you write it down for ULC, you can multiply it by R times UL on the left. And when you then subtract the two equations from each other, you will realize that this term just disappears because it's there in both equations, and it cancels each other out. What you end up with is this here, yeah. So this comes from the multiplication on the left side, and well, this is the kinetic energy operator that you have there. And on the right-hand side, you have the energies, the energy parameter, and the eigenenergy of the core electron, and times some scalar product, actually. And this integral on the left-hand side, well, it looks totally complicated, but it's not. You can solve it by integration by parts, or you can just use Green's second identity, and then you realize you get two terms out of that. And in one term, you will see that ULC at the Muffin-Tin boundary, and in the other term, you will see the radial derivative of this ULC at the Muffin-Tin boundary. So if these two are zero, then everything here vanishes, is zero, and this means that this scalar product on the right-hand side is also zero. Yeah? So this actually means they are orthogonal. Yeah? For the U dot, the proof goes analogously. Yeah? So, so I told you this orthogonality actually allows us to determine the core electron wave functions separately from the valence electron wave functions. And let's have a look at how we do this. We actually represent the core electrons on a radial mesh for each atom separately, and we treat them in a fully relativistic way. So actually, this is a little bit wrong, because this is the scalar relativistic. No, actually, it is a non-relativistic equation here. And so actually, we calculate the valence electrons, the valence electron use in a scalar relativistic way. So this already a simplification here. and for the core electrons we use the fully relativistic treatment. So, and the valence electrons, as mentioned, we represent by the LPW basis in a scalar relativistic way, and so the main difference between scalar relativism and full relativism is that in scalar relativistic treatments, spin-orbit coupling is not included, but we can include this afterwards. Yeah? So in the calculations, you can switch this on. Actually, this assumption that the core electron wave function vanishes in value and slope at the Muffin-Tin boundary is only approximately fulfilled. Of course, it may reach out of the Muffin-Tin sphere. Yeah? And so the idea that we have an orthogonality to the core states, well, it's a good approximation. Yeah? But for some states, the semicore states, they are less localized in the Muffin-Tin sphere and reach out of the Muffin-Tin sphere, and then this may lead to problems, to so-called ghost bands. So let's have another look at the LAPW basis, at another aspect, and this is the linearization. And so we saw that there is this K-max cutoff parameter with, that you can use to systematically extend the basis, at least in the interstitial. But of course, in the Muffin-Tin spheres, you have this U and U dot, and nothing beyond this. But if you want to express some function at an arbitrary energy E or epsilon, then you can see, you write it down as some power series or so, and then, well, higher order terms are missing. Yeah? You get 0 in first order term, this is a linearized description, and but the quadratic term is not there. So, and the error that is due to this linearization, we call the linearization error. But actually, for most materials, this is a very nice representation already, and we don't need to go beyond this. Yeah? So, but there are ways to overcome this in LAPW. So we can extend the basis set by other functions, so-called local orbitals. And these local orbitals are functions that are only non-vanishing in the Muffin-Tin spheres, and they consist also of this U and of the U dot, and of another U that well, is special to the local orbital. So a third radial function is there. And one typically uses these local orbitals to describe semicore states. And well, these A, B, and C coefficients are again calculated automatically by enforcing zero value and slope of the Muffin-Tin sphere boundary here, and also a normalization of the local orbital. So we can construct different local orbitals with these, and most common are the local orbitals I call semicore local orbitals, SCLOs, that can be used to describe semicore states. And there we just use as a third radial function also a U, so a solution to the radial Schrödinger equation or scalar relativistic Dirac equation at an energy that is near to the semicore state. But we can also choose energy parameters that are above the Fermi energy and above the energy parameters that we use for the LPW basis functions. And then I call this a higher energy local orbital. And this may be a good addition to the basis set if you use methods that go beyond DFT, like GW. So in GW, you typically have a sum over unoccupied states, and you also need to represent them. Yeah? And you can also have a higher energy derivative as a third radial function. This we call the higher derivative local orbital. And well, you can assume that you put such a local orbital exactly at the energy parameter of the LAPW basis function. Then you get a nice representation in a broader energy region. Yeah? So, but we can extend the LAPW basis functions even with other, well, in a different way. And so if we want to treat film systems, thin film systems, then we actually define vacuum regions above and below the film. And in these regions, we also have U functions, this UVAC and this UVAC dot. And well, they are also solutions and energy derivatives to the vacuum potential, yeah, also at energy parameters EVAC, yeah. And here you have to know that well, the way we define a film, it's actually rather efficient, yeah. I mean, in plane waves codes, you typically have such a slab calculation that where you just have a very large unit cell with a giant vacuum region in there. But we have an efficient treatment of the vacuum. So our unit cell only goes as far as there are atoms, mostly. So this is the D. But we have to extend the unit cell a little bit for the definition of the G vectors that are perpendicular to the plane of the film. And, well, we can ask me afterwards if you want to why this is done. And so just remember, there's a D tilde and a D. Both can be varied in the input file. And but you actually, well, I never touched them. So I guess you also don't have to do that. Yeah? And the vacuum parameters are also, well, you can find them in the input, but you will probably also not change them. So now let's come to the representation of the density and the potential. So, of course, we have this partitioning of space into interstitial region and Markov-Tin spheres, and in the interstitial region, we have a representation by plane waves again with these expansion coefficients rho g. And in the Markov-Tin sphere, we have a representation of with radial functions rho L alpha times spherical harmonics. And this is actually not true because in reality we have symmetrized versions of plane waves and spherical harmonics here. And for the plane waves, these are called stars. And for the spherical harmonics, these are called lattice harmonics. Of course, this expansion of the plane wave part also has cutoff parameters. They're called Gmax for the density and the potential, and Gmax XC for the exchange correlation for potential. So let's have a look at the effects or the choices that you have to do in practice then. So if you consider a plane wave and expand it in terms of radial functions, these are spherical Bessel functions times spherical harmonics on the Markov-Tin sphere boundary, you see, well, they look like this, the spherical Bessel functions. And well, when you have a look at, well, large L, then you see for larger L, like this L equals 8, for small k times r, so r is the Markov-Tin sphere radius and k is k plus g for the FLAPW. This is nearly 0. So actually you don't need to have some Markov-Tin counterpart for these L channels there. But actually we can go a little bit further, and there's a rule of thumb of how much you need, and typically you need an L max of 8 to 12, and this should be about k max times r Markov-Tin. So actually this equation is used to calculate this K max. I'll give you a guide of how to choose the K max. So let us have a look at what this means. I go to a little bit smaller values like 4. So the yellow curve here, so the yellow spherical Bessel function is the one for L equals 4. And if you go to Kr equals 4, you are about half of the first maximum here. Yeah? And if you go to 6, then this is the blue dashed line. You're also at half of the first maximum about. Yeah? And it turns out that this is actually already a nice value where you can say everything beyond this we don't need. Yeah? It is converged. This is what practice gives you. So then we also have a reduced L cutoff. This is for calculating the contributions to the Hamiltonian originating from the non-spherical part of the potential. And this is actually typically L max minus 2 and well, at most 8. So we need this large L max cutoff parameter mainly to get the kinetic energy right and to get the overlap matrix right. But the physics, the potential, and so plays at lower L values. So then there are Gmax and Gmax XC. And Gmax is a cutoff for different functions. So for example, for the charge density or for the potential, but also for the step function. And this is a function that indicates the interstitial region. So it separates interstitial from muffin-tin spheres. And it turns out that the potential and the step functions have infinitely many plane wave coefficients. Bad, because we have to calculate such matrix elements in the Hamiltonian, and if we have infinitely many plane wave coefficients in both of these functions, then there is no clear idea of where to choose the cutoff. Yeah? But it turns out that a cutoff that is chosen like this, so Gmax is larger than Gmax XC, and this is larger than 2 times Kmax, is already enough. Yeah, so typically we set Gmax to 3 times Kmax and Gmax XC to 2.5 times Kmax, about that. So now there's a question how to choose the energy parameters. And there are automatic ways to choose them. So you don't have to plug in a certain energy directly, but you have to make the choice of what recipe to use. And here I plotted the linearization error in terms of the difference of the perfect total energy with respect to the total energy that you actually get from some energy parameter. And you see, well, the best total energy that we get is down here at 0. You don't get anywhere near that for this system. This is cerium, and I chose it because it has a large linearization error. And so there are different ways of how to choose the energy parameter. Here you see the atomic energy parameter. It's quite far away from the optimum. And the so-called energy center of mass, well, it's a little bit nearer, but also not perfect. We typically use this atomic energy parameter because it's kind of stable. Yeah, it's it gives a nicer convergence behavior, and where we can control the linearization error if it is a problem by adding local orbitals or so. Yeah. So then there's a question: how do we choose the muffin-tin radii? So there is no single best option. So it depends on the material. Of course, in different materials we have different bonding lengths, And so we cannot say, copper always has a muffin-tin radius of 2.35 atomic units, although mostly it is like that. And but it may be that you have some copper oxide or so where suddenly some other atom is very near to this copper. What you have to keep in mind is that if you want to compare different calculations, like the total energy that comes from these different calculations, then beyond the one parameter that you want to change from one calculation to the other should be identical, especially the muffin-tin sphere radii. Yeah, so so assume you want to calculate a lattice constant, and then you do total energy calculations for different test lattice constants. Keep in mind the muffin-tin sphere radii have to be identical. Yeah. So for large muffin-tin radii, you have faster calculations. This is because you can choose a smaller K-max value and therefore a smaller LAPW basis set size. But on the other hand, the linearization error is larger. If it becomes a problem, well, not so good. You need fewer semicore local orbitals because the semicore states are more within the muffin-tin sphere if you have a large muffin-tin sphere radius. But keep in mind that some quantities are only evaluated in the muffin-tin sphere, like, for example, magnetic moments at some atom. Also, the relativistic treatment, the scalar relativistic treatment is only done in the muffin-tin sphere. Or if you calculate LDA plus U, the U parameter is applied only in the muffin-tin sphere. Yeah? For smaller muffin-tin radii, you have slower calculations, but they are more stable. You have a smaller linearization error, but semicore states may mean a larger problem, so you need more semicore local orbitals. But on the other hand, you have more space available for structural relaxations, like if you want to move the atoms around. And yeah, of course, if you want to move the atom, it is important that the muffin-tin spheres don't crash into each other. Yeah? Then this is an illegal setup. So let us have a look at what semicore states actually mean. Here we have the band structure of vanadium, and I calculated this with muffin-tin radius of 2.25 atomic units. And here I write how many electrons from the core electrons reach out of the muffin-tin sphere. And let's reduce this muffin-tin sphere radius. Then we get that. So you get this very flat band here. And this is actually a ghost band. Yeah? It's not yet a problem. It's only for if you want to visualize the band structure, then maybe you go only to 10 electron volts above the Fermi energy. Yeah? But now I reduce this even more to 2.17 atomic units, and you see more and more electrons reach out of the muffin-tin sphere. More and more core electrons reach out of the muffin-tin sphere. And the state goes down in energy. Yeah? And we can go further, and it goes even more down. And then let's go to 2.15 atomic units. We get an error. Yeah? Because in this case, suddenly this ghost band is low enough such that it gets occupied. And then you have these states occupied on the one hand as core electrons and on the other hand as valence electrons, and this is a big problem. Your potential will get destroyed, and you cannot deal with this anymore. Unfortunately, we don't have an error message. You have a ghost band. This is a problem. Solve it. But this error message is differ to problems with solving the Dirac equation, and this error message can have also other causes, and you can also have other error messages that come from semicore states. Too bad. So, but have an eye on that. you should look at how many electrons are lost from the core if you think that this may be a problem. So, if you put in semi-local orbitals, you remember this plot with 2.16 atomic units. We go back. So it had this ghost band here with semi-local orbitals. Well, this ghost band is gone. Yeah? Now, let's have a kind of a theoretical look at the linearization error. And I have to speed up a little bit. So this is again for cerium. Here I just plot the linearization error as a representation error. And for cerium, you see there's a core state here, and the LAPW description is orthogonal to that. But you can see around the energy parameters with LAPW, you have a certain energy range where the description is nice, but this can be extended by adding local orbitals to the LAPWs. For vanadium, what we just had, this is different. The semi-core state reaches out of the muffin-tin sphere, and therefore the LAPW basis is not really orthogonal to it. And well, if we would add then local orbitals to overcome the linearization error, we would get an even nicer description, and the error that we just saw would be visible even earlier. Yeah? But what you see here is that with these helo-type local orbitals, you can systematically increase the, or make the representation better for higher energies. And also for the higher derivative local orbitals, it is more like centered around the energy parameter. So these are about the largest effects that I saw from the linearization error. Probably there are larger ones and also smaller ones. Here you see FCC cerium, and I calculated lattice constants, first with an LAPW basis, and then with LAPW basis sets that are extended by local orbital basis sets. And you see for the sole LAPW basis, we get a dependence on the muffin-tin sphere radius. And this can have an effect like 1.6% of in terms of the lattice parameter. So this is about the accuracy of LDA or GGA. Yeah? So LDA and GGA are typically where they hit the experimental lattice constant, but are way like 1 to 3%, something like that. But for most materials, this effect is much smaller. Here you see rock salt, where it is 0.4%, for example. And then you can also look at the band structure. And of course, we choose the energy parameters such that the occupied states are well described. But for the band gap, for the band structure, you also want to describe the unoccupied states. And then you can see rather large effect, for example, for argon, for an argon noble gas crystal. The band gap can be reduced by 19% by adding these local orbitals. So this is the effect of the linearization error. So let's go to using FLIR. So in FLIR we have a two-step approach, and because the input actually requires many parameters, but we only want to provide the few parameters that we really need, like setting up the unit cell and the atom positions. And for this we have an input file generator called impgen, and the input for that looks like this. So we have a comment there. We define the lattice system. We can also define the Bravais matrix here. We define a lattice parameter. We say how many atoms there are. There's 2. And the atomic number of these atoms, so 11 and 17. This is sodium chloride. And where they are in the unit cell. So we use them by calling impgen and piping this input file into the program. So it expects input from the terminal actually. So if you want to learn more about the input file generator, then there is this option -h, for a list of commands. Some commands are listed here, for example, -explicit. There you get more output into this imp.xml file, or -noco for aspects related to non-collinear calculations that can also be plugged into this imp.xml file, this real input file for FLIR. Gen and para. So typically we use this atomic energy parameters, and for this we only define the main quantum number. And but we can also have more control about the energy parameters, and for this we need another file. This is called npara. Yeah, and there are more. So let's have a look at this imp.xml file. So it consists of several sections here. So first there's some syntactic sugar here, and everything is enclosed in this FLIR input XML element, and there's a section about a comment, like FLIR is cool, or whatever you want to plug there. And then there's a section about the calculation setup, the cell, the unit cell, the exchange correlation functional, the atom species, the atom groups, and the output. If you invoke FLIR and want to let it run on a certain input, just call FLIR, or FLIR MPI if you have a parallelized version of FLIR. And you don't need any, you don't need to specify here any file. It will always use the file that is in the working directory. Yeah? Of course, here also you have this -h command line option to see all the FLIR modes. So in this calculation setup section, you can define the cutoff parameter Kmax, Gmax, and Gmax XC. You can also specify how many bands are to be calculated. 0 is just a shorthand for use a default number, like what you guess is the right thing. Yeah? Then you can set some parameters for the self-consistency, like the number of iterations you want to perform. If you want to set a conversions criterion, you can do this here. This is actually typically by default 10 to the -5. Yeah? So this is not 0 anymore. The mixing scheme in this self-consistently loop that you remember from Mariana. And then you can specify how core electrons are treated. You can specify magnetism there, how many spins there are in the system. You can specify how the integration over the Brillouin zone is done, like how many K points there are, if there is or how large the smearing is for deciding what states are occupied to what extent, how many valence electrons there are, and so on. There are also more inputs there that you will see. Yeah? Then there is this cell section. There you first specify a symmetry file, or you can, well, there are the symmetry operations in there, like a list of matrices. This is. Then you can have the Bravais matrix. Well, this obviously is some FCC crystal, and afterwards there is a section for the exchange correlation functional, where you can specify the exchange correlation functional that you want to use, like in this case PBE with GGA functional. Then there's this atom species section, like we want to have sodium, and sodium has this atomic number, and we use one core state. It has no magnetic moment. Here we set the Mafontin sphere radius, the number of grid points on the radial grid, and the logarithmic increment for this radial grid. Probably don't have to touch this as long as you're not a very advanced user. Then you set here the atomic cutoffs, like this L-max cutoff and this L non-spherical cutoffs I told you about. The energy parameters in terms of main quantum numbers. And you can also list here the local orbitals that you want to add to a certain atom species. And then we have atom groups. This is also specification of the atoms, but here you have the atom positions. And these groups, well, they can contain several atoms that are related by symmetry operations. So all of these atoms that are in one group can be mapped onto each other by symmetry operations. And here you can also set whether you want to do some structural relaxation in some direction or what else. Then there's an output section where you can specify like, yeah, I want to calculate a band structure, or yeah, I want to calculate some density of states. And you can also parameterize these calculations. Yeah, more you find on FLAPW. Yeah. So, one of the last slides, sorry, I'm over time. So you get certain types of files when you use FLIR. And the files are different for whether you compile with HDF5 support or without HDF5 support. So HDF5 is the hierarchical data format 5, and it's a certain type of specifying files. So you have this imp.xml file, the symout file with the symmetry operations, the sympara file. The cdn.hdf file is the charge density file. Then there is the mixing history that you can also get, and you can get additional input files for special calculations. And of course, there are also out files like out, inf, or out.xml. And without HDF5, the cdn.hdf file here is a cdn1 and cdn with other numbers files. So cdn1 always has the last density. And also here you have stars and WKF2 files, and these you have to remember because they depend on many parameters. So if you do some, for example, they depend on the atom positions. So if you do some structural relaxation, don't forget to delete them. Yeah. So WKF2 is actually the step function, and stars are the stars. Yeah? So this is some further reading. If you want to know more, then there's a very nice book by Singh about the LAPW method. Then there's this initial publication by Anderson and an extension to films by Krakauer. Then there is a nice paper of how to calculate the potential by Weinert. And if you are interested in the historic predecessor, this is the augmented plane wave method, then you read this paper by Slater. And if you're interested in local orbitals, then read this paper by Singh. This is where they were originally proposed. Or, these other types of local orbitals, or the analysis on the linearization error, you can see in these papers. Yeah. Well, I end this here.